Okay, we're going to move on to something called one-sided limits. And let me start you out with an example. If you were to graph this function, absolute value of x minus 1 over x minus 1, basically the graph looks like this. And actually, if you graph it, you're going to find that there's actually no value at 1 here for those. So what's going to happen is as you approach positive 1 from the left, you'll notice that the graph just stays at negative 1. And if you approach positive 1 from the right, you'll notice the graph just stays at 1. So the notation that we use to describe the limit, if you see this little negative right here with the 1, that tells you that we're finding the limit of this function as x approaches from the left. So here's 1, and so if we approach 1 from the left, remember the function's staying at negative 1. So this limit would actually equal negative 1. Okay, but if you look at this other limit here, this other one-sided limit, this limit we're approaching 1 from the right. That plus means we're approaching 1 from the right. Well, if we approach 1 from the right, notice that the function just stays at 1. So this limit is 1. Now, the one-sided limits exist. You know, the left-hand limit, which is what we call this, is negative 1. The right-hand limit for this function as x approaches 1 is positive 1. But the limit itself does not exist since the right-hand and left-hand limit disagree. Okay. Now another example of where you could have left-hand limits and right-hand limits but not have the limit itself might be a piecewise function. So let's take a look at this. All right. So this line right here represents x equal 2. So that's the line x equal 2. Now it says here if we're to the left of x, if we're to the left of 2, we have this linear function 2x minus 3, which is this function right here. Okay. If we equal 2, we get 5. So if we equal 2, we're up here, we just get this 1 point, 2, 5. And if we're greater than 2, we get like this piece of a parabola, 1/2 x squared plus 1 for greater than 2. So that would be this piece here. Okay, now let's look at the graph. If you approach 2 from the left, if you approach 2 from this side, you're actually going to be approaching through this piece. Okay? Well, the limit is actually the left-hand limit. In other words, the limit from this side is going to be what you would get if you plugged 2 into that function. So the limit from the left is actually going to be 2 times 2 minus 3, which is 1. But if you approach 2 from the right, if you approach 2 from this side, you're actually going to be coming in from this function. And as you approach from this function, if you plug 2 into here, you would get half of 4, which is 2, plus 1. So that would give you 3. So the right-hand limit is 3. The left-hand limit is 1. Well, since the right-hand limit and the left-hand limit are not the same number, then we say the limit itself, or if you prefer the two-sided limit, does not exist. Okay? Notice that the functional value is 5. Not that that really affects the limit, but the limit does not exist because the left-hand limit and the right-hand limit are different values. Okay, so this just describes the notation that you use. The limit of a function f of x as x approaches c from the left is given by this notation. Notice the little minus by the c. And the limit as x approaches from the right is given by the little plus here. And then there's an existence theorem, which kind of reiterates what I just said, that if f is a function and c and l are real numbers, the limit of f of x equals L if and only if the left-hand limit equals L and the right-hand limit equals L. So in other words, in order for a limit to exist and be a real number, the left and right-hand limits must also equal the same number. So we showed earlier, in an earlier example that this limit was 3. Well, since we know this limit is 3, then from this theorem we know that if this limit's 3, then the left hand and the right hand limits must equal 3. So the left hand limit must equal 3 and the right hand limit must equal 3. Okay? We showed earlier that this limit, the left hand limit of this, was -1, and the right hand limit of this was +1. So since those limits are not equal, then we know that the limit itself does not exist, because for this limit to exist, these two limits must be equal. They must equal a real number and be equal. Now, if you take a look at this graph here, you'll see that if you want to take a look at, here's 1 right here. That's that dotted line, x equal 1. If you approach 1 from the left, notice how the graph decreases without bound. So the limit as x approaches 1 from the left is -infinity. And then as you approach 1 from the right, notice the graph increases without bound. So the limit as x approaches 1 from the right is +infinity. So since neither of these limits exist, then the limit itself does not exist. Now, read this note here. If both of the one-sided limits were plus infinity, we could say that the limit as x approaches 1 is infinity, but the limit still would not exist. That's just a special way to say it does not exist. Because for the limit to exist, this has got to equal a real number, not infinity. And you can practice on these. The answers are given below. And what I suggest is you look at their graphs. And then you can check their answers with the graphs. Okay? There's several of them there. So you can practice on those problems and see if you can get the answers that I gave there. Now, I want to wrap up by talking about evaluating limits in general. So, you know that if you have a polynomial, you can generally just, and you want to evaluate that at a limit, you just plug that number into the polynomial. If you have a rational function, and by plugging in, if you plug the number in and you get 0/0, which is what we would get here, then you want to look for a way to simplify this. So a way to simplify this would be to factor it and then cancel the common factors. And then you can plug the number in here and get 3/2, which is 3/2. Okay? Now, you don't have to factor and cancel here. You could. It would still give you the right answer. But you don't have to factor and cancel here. The reason is if you plug 2 into this function, you don't get 0/0 like you did over here. So here, if you plug 2 in, you actually get 4/3, which is a real number, so we can just plug in there. Now, if you want to evaluate this limit, now notice it says evaluate the limit as t approaches, well, it should say x, but as x approaches 1 from the left, then what I would do here, you know that when x approaches 1, the bottom's going to go to 0, so this thing's going to kind of what I call blow up. But the question is, does it blow up in the negative sense or does it blow up in the positive sense? Well, what I like to do here is I like to just pick a number that's very close to 1 from the left, like say 0.9. Okay? Now, so if you plug 0.9 in here and you get a positive number, then I know this goes to +infinity. Had I gotten a negative number, I would have said it goes to -infinity. So anytime you have a constant on top and the bottom goes to 0, it's on a one-sided limit, it's going to go to plus or minus infinity. You just have to do a little investigation to see. This one says the limit of absolute value of x over x as x approaches 0 from the right. Well, that means positive numbers. Well, we know the absolute value of x, if x is a positive number, is just x. So in that case, the limit would be x over x, which is 1. So the limit would simply be 1. Now this says same function but from the left. Well, the problem with the function, what you get is if x is a negative number, then the absolute value of x is opposite that number. So you actually would have negative x over x, which is negative 1. So the limit of negative 1 as x approaches 0 from the left would be negative 1. And then here's an example of where you need to rationalize. Now this one's a little bit tricky because you've got two variables here. But if you let delta x go to 0, the top's going to be square root of x minus square root of x over 0. So you're going to get 0 over 0 here. So you know you got to do something to fix that. So notice here I'm going to use the conjugate. This is the conjugate of the numerator. So I'm going to multiply the top and bottom by the conjugate. Now when you multiply this out, you get x plus delta x minus x on top. So the x's cancel and you just get delta x. Well then you have delta x over delta x, which is 1 as long as delta x does not equal 0. So you just get 1 in the numerator all over this. And now if you let delta x go to 0, that's just going to wipe out that term. So the bottom's going to be 1 over square root of x plus square root of x. And of course square root of x plus square root of x is 1 over 2 square root of x. Okay. And then here's another one. This one's a little tricky. What you have to do here is you have to get rid of these fractions that are on top. So here I'm going to multiply. By the way, if you plug delta x, if you let delta x be 0, you're going to get 0 on top and 0 on bottom. So I'm going to multiply the top and bottom by the common denominator, x times x plus delta x. So when I multiply this term by x times x plus delta x plus delta x cancel, and I just get an x. When I multiply this term by x times x plus delta x, the x's cancel, and I just get x plus delta x. And then I have to subtract that quantity. So I have x minus this quantity, so the x's will cancel, and I'll have minus delta x. And on the bottom, I'm going to have delta x times this quantity. So now I have minus delta x over delta x, but that's just going to be minus 1 over this. And now I can find the limit of this as delta x goes to 0. Remember, since delta x is going to 0, it's not going to affect x. So let delta x go to 0, and you just get minus 1 times x, or minus 1 over x times x, which is minus 1 over x squared. So I know these last two are a little bit different because I threw two variables at you, but remember the x is unaffected by what delta x is doing. Now, you can read these final notes here. Okay, so freeze the video if you need to and read the final notes. But here's a couple of other examples. And so if you want to find the limit as x approaches infinity, we'll talk about that later. But take a look at these last two examples here. This is kind of what I was telling you a while ago. You know that as x approaches 1, the top's going to be a constant and the bottom's going to 0. So that means these have to go to infinity or negative infinity. Well, the best way to figure out where they go is to plug a number in on each side of 1 so that you can get an idea what the value is going to be. So if I plug a number to the left of 1 in, I got a positive number, so I'm going to say that's positive infinity. And when I plugged a number just to the right of 1 in, I got a negative number, so I know that's going to be negative infinity. Okay. Now, if you want to evaluate it at negative infinity and infinity, then just plug very large numbers in. So if you plug a very large number into this, you're going to find that this limit's going to be negative 1, or a very large negative number in, that's going to be negative 1. And if you plug a very large positive number in, you're going to see this is very close to negative 1. So these limits are, this limit is actually negative 1, and this limit is actually negative 1. And that's pretty much the end of limits. Continuity comes next.